I'm Cathy Wyss. Catherine sounds very formal. I think only my mother's ever called me Catherine. Which is fine. And you'll notice in this title I left off the machine learning. Basically writing these slides, I realized I had quite a bit of material and I didn't want to go over time, so I actually have left out a little bit the machine learning, so I won't give an overview of that. But I do have a very interesting case study for SQL Server 2017 and Python in particular. Okay, so I'll just start about me. I got my master's in Edinburgh in 1997, so that tells you how old I am probably about, very old. And my PhD in databases at IU Bloomington in 2002. That was database theory, actually. I did query languages. And then for actually 7 years, I was an assistant professor of computer science and informatics at IU Bloomington, where I taught databases and also information representation. And then I took some time, both to raise my daughter and also to do something completely different, and that is I made a little publishing company and wrote some fiction books. So I write mystery stories and science fiction, and I'm self-published on Amazon under the pen name Wyss, if anybody's curious. Little plug for myself. And now I'm a data analyst at the IU School of Medicine in the Medical and Molecular Genetics Department and the Human Genomics Division of that department. So a little bit about what MMGE does, and in particular what I do in MMGE, since that's, of course, what I can speak to best. So one of the big things we do in MMGE is biobanking. And one of the projects, or the project rather, that I'm going to talk about today is called Fluidigm. Fluidigm is basically a machine that is used for fingerprinting DNA. So one of the things in biobanking is you have a lot of specimens, which may be, things like brain tissue, blood, or DNA itself, for example, if it's been extracted, and you want to, distribute them to research people or accession new samples, get them in, and so one of the things that you're interested in is quality control and identity. So fingerprinting the DNA when you have it gives you a way of, talking about the identity of a sample in a concrete manner. The department also is into disease research, and so for example, Parkinson's, we have a couple projects that I work on. One is the widespread recruitment database, which is looking for people who may have Parkinson's disease in their family, and they get in conjunction with the Michael J. Fox Foundation and via us. And another project that we're doing also with respect to Parkinson's is wearables, which is an Internet of Things project. And essentially, the subjects get watches, kind of like an iWatch in terms of size, that measure their biometrics, so their heart rate and their motion. And then researchers can use this data and hopefully gain some insights. So what I do is I do mostly data migration, integration, and analytics. And one thing that I've been very happy to do in this position is I actually was able to start projects fresh. So I actually was able to design a database, implement the database, and then implement workflows around it, and even all the way up to visualization and reporting. And often when you come into a company, you're inheriting a project or you're inheriting a code base, and you don't get that opportunity. So that's one thing that I've really enjoyed about this position, is the ability to follow a project through, basically from beginning to realization. So this is SSIS, it's SQL Server Integration Services, and what it is a workflow manager. So this is an example of what I'm working on every day. And I guess I wanted to show this because a theme of this talk is to use the best tool for the job, which we already heard that in another talk earlier this morning. You want to utilize the best tool for your particular task, whatever that might be. So SSIS, we are a Windows shop, so we use the SQL Server suite and all the Microsoft tools that come with it. And SSIS is one of those. And really, even though it's the SQL Server suite, it's just a general purpose workflow manager. So this is one of the workflow that I set up. And I don't know, you probably can't read any of this, but this is a Python process that I call. There's a lot of SQL. This here is an ETL, or extract, transform, load, which you also heard about earlier today. And then there's some C++ in here as well, and I'll talk about that in a little bit. But essentially, SSIS allows me to incorporate all those different technologies into one workflow that runs for Fluidigm. And that's kind of the thing I do every day. Okay, so overview of this talk. One thing you may be wondering is why use SQL Server? And when I say why use SQL Server, I mean why use a relational database? Because there's nothing particularly special about SQL Server. You could use Oracle, you could use Azure, which is SQL Server, but on the cloud. You know, so why use a relational database? Why not use a document store, a data lake, flat files? You know, and so this is kind of what I'm going to address in this talk. And I guess one of the gentlemen before me said, you know, you have to consider your resources when you're choosing which technologies to use. And I'm a resource, and I like relational databases a lot, and I'm very familiar with them. So, of course, that's one reason to use it. It's not the only reason, though. And then there's another question, and that's why use Python, because I tend to use Python. I make APIs, for example, to the database, and I use Flask for that. And I'd say I probably don't have to justify that an awful lot to this, because it's pretty clear that Python is growing and has an awful lot of interest, a lot of activity, a lot of maintenance in its package base. So really pretty obvious why you'd want to use Python. Okay, so I guess in order to talk about what technologies one might want to use and decide whether to use SQL Server or some other database type technology, or even not a database technology, I need to talk a little bit about the project. So I'm going to talk about Fluidigm, which I mentioned earlier. And Fluidigm has to do with the biobanking that IU, and in particular our department, is involved with. And so these are large initiatives. They're usually statewide, potentially even nationwide. And you may have heard of Precision Health, that initiative. The IU Health Initiative, which I think is part of Precision Health, but maybe a little bit different. We also have NICRAD, and I don't even know what that stands for. But it's also a biobanking project right now. I think we have probably 60,000 specimens with it. But overall, in our database, we have 2.2 million specimens that we're storing. And we're not only storing the physical specimens, we're storing the data on those. And so that gives you an idea of the scope of this type of project. So to talk a little bit more about fingerprinting, essentially what Fluidigm, what the machine does, is it takes DNA, looks at 96 SNPs, SNPs, which, you know, sometimes I might call them assays or locations, but essentially they're recognizable places on the, or markers on the DNA, and you genotype those 96, and there are types XX, XY, XY, and then no call or absent. And what you get when you genotype those 96 SNPs is you get a fingerprint for that DNA. We've chosen the SNPs that we fingerprint such that if two specimens were to match on, say, 15 or more of these, we're really quite certain they're from the same person. So these are distinguished SNPs, and it's really part of what we want to do is check identity. So we want to make sure, you know, when a specimen comes in and someone asks for it, what goes out is the same specimen that came in. We want to check identity. And we also want to do things like check, you know, is the genetic gender of the person the same as the reported gender, this kind of thing. And this is the type of thing we can do with these SNPs. So, so it's just called fluidiming, what this machine does. And we use it for, eventually we're going to use it for accessioning, which is when you bring the specimens in. Right now we're using it mostly in distribution, which is when the researchers ask for these specimens. Essentially, the databases we have not only talk about where the specimens are located, we also have attributes of the people that these specimens belong to. So researchers can go and they can ask for, you know, we need 1,000 people that have, you know, that are positive for this type of disease, or we need 1,000 people that, you know, half male and half female for some reason. So basically, you can pick characteristics of the specimens according to what research you're doing. Oops. So this is just a bit more about Fluidigm. On the left, there's a plate, or if I can read it. It's involved in plating. It's basically what they use to make a plate of samples that would go into the machine. And then on the right, which I guess is your right, basically is the type of data that comes out of the machine. Essentially, there's the 96 SNPs in one direction, and a plate holds 96 samples, so that's what the other dimension is on that output. So that's what it looks like. And then this is interpreted in terms of the genotypes. So you have 96 times 96 data points, essentially, for each. So that's not all that Fluidigm had for data sources. So we have, as I say, the qualitative characteristics of the subjects that belong to these specimens. And those are most of them are in an Oracle database called, that we call Encore. Some of it's in a SQL Server database, some of it is legacy data that's in an Access database. There's also the machine output, and that tends to be in flat files. So it can be fixed width or CSV. The ones that we work with are CSV. And then there's lab data, which is the data in the process of fluidiming and distributing these specimens. So that's CSV, flat files, or Excel spreadsheets. So a big part of the project was data integration. So taking all these disparate sources and storing them, housing them in one place so that I could query against all of them in the same manner, uniform manner. Oh yeah, we also had reference genotypes, which was, you know, there are other sources that you can get genotypes from, GWAS, for example, and we had those in CSVs as well, so I need to load those. Okay, so the types of questions we were interested in, does the sample distributed match accessioned? I mentioned that. How concordant are two samples? Concordance was a tricky concept in our context, and we had to actually sort of make our own definitions for it. But loosely speaking, concordance is just, you know, are the samples from the same person or not, or how likely are they to be from the same person? Is the genetic sex of the sample the same as the reported sex? Does a particular sample really belong to that subject? So if we fluidimed 5 specimens for a subject, and a 6th one comes in that's supposed to be for that subject, how do we compare that 6th subject against the 5 previous ones? Is the sample contaminated? Can we tell that from the data we have? And it turns out, yes, we can. Then there were also some metrics sort of about the process itself, an example of which might be how fast is the lab turnaround time for this process, the fluidiming and the distribution. Okay, so it's not only the fact that I was fairly well versed in the SQL Server suite, but also SSIS is good at integrating these various sources, and you'll notice they were in Excel, for example, because we're a Windows shop, or CSV, and Oracle is a relational database. So SSIS is very good at integrating actually all of those sources that I mentioned in the previous slide. But after integrating them, I needed to come up with a database model, integrating them and deciding that SQL Server was what I was going to make, or a relational database was what I was going to use. And I guess part of the reason for using a relational database, at least, would be the entity relationship model. So on this model, you break up your domain into entities, which are basically things, and relationships between them. And it's very nice. So here I have 3 things that look suspiciously like tables, because the relational model is, of course, nothing but tables and links between them. And these are the 3 tables at the heart of the Fluidigm system. And early on, I realized, that this was the type of data we needed to keep. So the relation on the left, genotyping, that's a relation that essentially stores 1 record per plate. And it talks about things like the run date. The lab actually calls that plate, how many specimens were actually tested on there, and how many were NTC, or sort of just calibration specimens. It talks about the some cumulative statistics for that plate. So anything that's really an attribute of a plate goes in the genotyping relation. And in terms of how many we would see about those, our lab goes through probably 3 or 4 a day. They're hoping to ramp up to maybe 6 or 8. So overall, you'd see probably thousands of genotyping records in the lifetime of this project, possibly tens of thousands. So in the middle is genotyping specimen. So each plate has 96 specimens, and this is what represented here in this middle table. And there's probably, if there's thousands of plates being run, then there's 100 times that, or basically 100 or tens of thousands of specimens. And so a specimen might have such characteristics as it will have cumulative characteristics about its SNPs, so it'll have a call rate, for example, how many of its SNPs were actually given a genotype. It'll have things like a gender, so is it a specimen of a male or female? And these naturally kind of go with a specimen. And then over on the right here, I have the genotyping result, and this is the third sort of concept that I broke this into. And a genotyping result is essentially the actual genotypes for the SNPs for each specimen. So if you have sort of on the order of thousands of genotyping records, you'll have sort of tens of thousands of specimens, and then you'll have millions or tens of millions of the genotyping results, because it's 2 orders of magnitude more. So one of the strengths of the relational model is that it enabled me to break this up like this. If I had to carry around the characteristics of a plate with every single genotype, I would have doubled or tripled the size of the genotyping result relation, because I have all those extra characteristics that I'm carrying around with it. On the other hand, I can break it up like this and just use foreign keys, essentially, to relate to each other and to get the information back out. And one thing it's a little bit difficult to do in document databases, but it's very natural in relational databases, is joins. So rejoining these relations to actually get all the attributes of everything that you want is what a relational database does best. And down here, I just have the subject relation, just to give you an idea. There's probably tens of thousands of subjects in our database right now. Okay. So another decision that had to be made in terms of this big relation over here is, do I store it the way one might think of the data, which is as you know, a wide array of those 96 SNPs, and each one has an XX or an XY or a YY. And wide relations aren't actually that friendly in a relational database. I would say if you were manipulating this as a Pandas data frame, you would probably want it to be wider and shorter, but in a relational database, you want it to be narrower and longer. And one reason why is you can index everything. So getting to any particular place in the longer relation is very fast. And writing queries on the longer relation as well is easier because you only have 3 or 4 columns to write the queries on. Whereas in the wider relation, if you're using SQL, you have to actually name all of those columns if you want to talk about their values. So, and this is roughly speaking, it's normalization, which is breaking the wider relations into narrower ones. And this is, it's basically kind of an unpivot. So I don't know if folks are familiar with SQL or the relational model, but, or Excel even, because Excel does pivot and unpivot. So in Excel, you can take a narrow relation, pivot it, and it becomes wide. Or you can take a wide relation and unpivot it and it becomes narrow. But really, it's storing one genotype for one SNP in each record. So just a little plug for SQL Server 2017, and Microsoft is not actually sponsoring me for this, so this is just my my own sort of things I found out about SQL Server 2017. So one thing that's nice is it's got full text search. So when we do have actual document data, you can essentially just plop it in there as text, and it'll allow you to search on that in your SQL queries. The really exciting thing, though, is now there's machine learning in SQL Server 2017. So Microsoft has kind of, well, they essentially frightened everybody by saying they were going to get into R, okay, and they kind of took over R a little bit. But, you know, it's still open, it's still free, it's still very developed, it's still open source, which surprised everyone. And now they're basically doing the same thing with Python. They're moving into this field. They see it as an up-and-coming machine learning platform. So right in your relational database with those tables, you can actually view these tables as Pandas data frames, and then use the Python machine learning classes such as Keras or Tensorflow or any of those packages that use Pandas as their data representation. And so going between the relational model and the Pandas model is very natural, and you can do this in SQL Server 2017. There's also a Linux version, which surprised me. So the big bad Microsoft has sort of come around in some ways. And I think I read that while they tend to sell, you know, hundreds of thousands of servers, I think the first couple weeks that they released SQL Server 2017 for Linux, it downloaded like 8 million times. So it's being used, and I mean, I haven't heard anything bad or horrible about it, so I think it's probably working. Oh, and you can Dockerize it as well, which is really cool. So SQL Server 2017 has Transact SQL. That's their version of SQL with some additional constructs. Just out of curiosity, how many folks in here know SQL? SQL? Yeah, everybody. Well, not quite everybody, but almost everybody. Excellent. So, so you probably know already that SQL is not Turing complete. So it doesn't have loops, for example. And Transact SQL puts the loops back in, but on the other hand, you can also write pure SQL without the loops. And one advantage of the pure SQL, or the select from where group by having clause, is that it's got the relational model underlying it, which enables you to optimize those queries extremely well. So essentially, the user just writes what they want. They describe the end result in SQL, and then the query optimizer goes away and optimizes it very, very well. You know, and that's a major challenge in some languages, because if it's Turing complete, then you don't have this very nice logical model underlying it, or algebraic model, rather. Now, unfortunately, I don't believe these are available in Linux, but the SQL Server suite of tools is sort of an end-to-end system of services and products for data analysis, and you know, everything from storage to so integration, storage, reporting, and analysis. And SSIS, which was that workflow manager that I showed a little bit, that just uses Visual Studio, their sort of big coding platform. Okay, so here's some statistics about Fluidigm. Genotyping, the plates relation, right now we have 380 plates that we've run in the 8 months that this has been up. We have 80,000 genotyping specimens. Now, the reason why that's not actually just 96 times 380 is because of all of the reference genotypes that are in the database. So a lot of those are reference genotypes. The genotyping results is about 3.5 million rows, and we have 50,000 subjects. So these aren't super impressive numbers. You wouldn't look at this and say, okay, that's big data, because it's, you know, really not. But I'm sure, you know, folks know that genotyping data and genetic data is just going to get more prevalent, not less. And so, as more people become have their genomes mapped, and as more fingerprinting is done, all of this data is really poised to explode. In fact, it is exploding. These are fingerprints that we're storing, whereas whole genomes, of course, are much, much, much larger. And then the Encore, which stores the attributes of our subjects, that's 2.1 million. That's our 2.2 million specimens, and that's in the Fluidigm database as well. I didn't take all of the attributes down, but I take enough so that I can map them to our specimens. So it's about 20 gigabytes large right now, which is, you know, it's large enough that that you need a database for it. It'd be kind of unpleasant to have to deal with that many Excel files, but it's not really, you wouldn't call it big data at this point. So a use case for the type of visualization and the type of sort of pairing SQL and Python would be something that just happened a couple weeks ago in Fluidigm. We had one subject, and we had 19 specimens that claimed to be for that subject that we Fluidigmed. And we wanted to know, are these specimens actually all from that subject? So our database, our Encore database was telling us that these 19 specimens came from that subject. We didn't believe it. And so we wanted to see, you know, to essentially try and group the specimens by their fingerprints and see if any were from the same people or not. And to sort of understand what this problem entails, you need to know about concordance. And this is just a measure of genomic similarity. If you have, you know, if everyone had 96 SNPs, that would be pretty easy. We could just basically look at it and say, which SNPs do they have in common? No problem. Unfortunately, what happens is not all the SNPs are genotyped for every person. And with the historical data in particular, sometimes there might be only 16 SNPs that overlap. There might be 64 instead of 83 or 96. So we had to define a notion of concordance. And so this term here, the rate, which I call support divided by overlap, that is what you would think of as concordance naively, which is basically just how much do they agree on versus how much are they both defined on. And then the adjustment is going to be because of the fact that we don't necessarily have all 96 SNPs for these. So support here in this little example with 10 SNPs support is basically where they agree on genotypes. Overlap is when they both are defined on those genotypes. And essentially you want to compute a weighted average of the rate and adjustment. And what we found in practice, so the adjustment is overlap divided by the total possible, or 96. And that basically penalizes, the rate can be quite high. So let's say they match on 2 out of 2 SNPs and they're only defined on, like one of them is only defined on 2 SNPs. Well, that doesn't really tell you very much because there's only 2 of those little assays that actually got matched, in spite of the fact that you have 100% rate of matching. So the adjustment is a penalty term for that kind of case, where you take the overlap, which in that case would be 2, divide it by the total possible, and that will tend to decrease the concordance of specimens that only have very few SNPs in common. And so we took a weighted average of the rate and the adjustment here, and what seemed to work best was about 0.8 times the rate plus 0.2 times the adjustment, so sort of reduce the contribution of the overlap by about 20%. And that's because when you get about 15 SNPs matching, you can be quite confident that this match is not a spurious match. If there's only 3 genotypes, it's very likely for any 2 specimens to agree on 1 SNP, and it's actually quite likely for them to agree on 10 SNPs even. But once you start getting to 15 or 20 SNPs, then it's not so likely that that's a random match. So what to use for this? It's sort of a question of, when I'm wanting to look at these 19 specimens, should I just dump them all out, load them into Pandas, and compute the concordance there, or should I compute it in SQL? Where do I visualize it? So just a sort of back of the envelope calculation. I don't know if that's very viewable, but basically when you do concordances, we wanted to do all pairs of concordances, and that's basically your n times n minus 1 over 2 term. That's how many distinct or unique pairs there are given n items. So it's really an n squared term that you're computing here. So for 19 squared, 19 times 18 over 2 is only 171. That's not very much, So in Python, we would have to do a full scan of the 80,000 specimens to find the ones we want. Then there's the n squared term. Then there's actually looking at the concordance, sort of running over the genotypes and seeing whether they match. And so this is sort of just a rough calculation of how many steps we might have to do for that in Python using a fairly naive algorithm. Now in SQL, the nice thing about SQL is these relations are all indexed. So instead of having to load in a CSV and then search it from start to finish to find the specimens, I can just go right to the specimens because I basically know their subject, and I can just use that index to find them immediately. And then this term is also a little better. But basically, it's the n squared term you can't really get away from. So neither of these is really better than each other. It's just that the SQL has a little bit better constants in front of the n squared term. And then visualizing the result. So I chose SQL to do the concordances in this particular case. Visualizing the result, I was thinking of a 19 by 19 heat map. So SSRS, the SQL Server reporting services, can do this, but what you end up doing is you make a table, a 19 by 19 table, and then you essentially have a complicated if statement for the color of every little cell. So you can do it, but it's very annoying. So not the right tool for that. Python, on the other hand, I like the graphics libraries a lot. We saw bokeh this morning, and I'm partial to matplotlib, and in particular Seaborn. So that's what I was going to use. So now this is tiny. It's probably insulting to put this up there and expect people to read it. But this is the SQL Concordances code. And so I did the calculation of the concordances in the database with a couple common table expressions and a couple functions. And essentially, what this does is it actually finds the specimens. And then what this does is puts together 2 copies of that, so the 19 by 19 specimens, and calculates the concordance for all of them. And the concordance calculation is not actually a loop. It's just a set identity, basically, or set equality. And it's a count of how many, it's a population of how many of the genotypes are the same and how many they overlap on. And so technically, I could have actually taken those functions and made them common table expressions and just have this be one query as opposed to calling user-defined functions, which always have an overhead. But I didn't want to put that on the slide because it was already big enough. Okay, so if I can figure this out, there's a little demo here. Oh my gosh, that's like tiny. I can't even read it. 10 minutes, okay. Okay, so that's slightly more readable. So basically, I was going to calculate the concordances in SQL and then do the visualization in Python. So in Python, I just want to import my libraries. So this RevoScale Pi, that's a Microsoft library, and it's essentially used for pushing a query to the SQL Server database and getting the result back as a data frame. So it's essentially a Pandas interface, really. There's the connection string, which are always notoriously irritating to make. But when they work, they actually work. Then here's the query. There we go. So there's just my query that I have. So I'm just setting that into a variable. Okay, so essentially I make the query into a thing that can go to the database. And then this Rx import, as I say, is going to push that query to the database and return the result. Now, why is this different than, PyODBC or SQL Alchemy? Basically, it's different for the purposes of this demo because it returns a data frame. So it doesn't return a record set, it returns a Pandas data frame that's already sort of compatible with Pandas. Okay, so that took 1.3 seconds, which, is fairly long. I didn't have it cached or anything, and it's actually running on this guy, who is a little underpowered anyway. So I'll import Seaborn. I'll pivot the data frame that I got. I could have done the pivot in SQL. I just decided to do it in Pandas instead, and then make a heat map. So there's my nice heat map. So what do you think? Are any of these folks related? Or are any of them the same person? We looked at this and we thought, no. We thought they were all different people, because no one really has very high concordance with anybody else. They're, essentially they're all kind of hovering around 0.5, which is probably not not sign. So essentially our database was incorrect and was listing these specimens under under the subject when it should not have been. So it enabled us to go and clean up the database and figure out what happened, which I think we're still trying to figure out what happened. Databases just have glitches sometimes, of course. There's the little map. So this was only 19 specimens, which is not super impressive. But one thing we wanted to do as well, and we want to do this every single time we load a plate, is we want to look through the entire database to see if we've seen those subjects on the plate before. And we also, at least once, wanted to look through the entire 80,000 specimens and see if any were actually of the same subjects. So, for example, maybe people who'd signed up on different studies and we didn't know they were the same person. And so that's more like, 80,000, sort of 10 to the 5, 10 to the 6 times itself. So that's more like, anywhere from billion, 10 billion to 100 billion pairs, depending on whether it's 80,000 or 100,000. So we wanted to calculate that, and in terms of using the right tool for the job, I considered SQL. I tried it in SQL. Now the nice thing about SQL is relational databases will run even if your result doesn't fit in main memory. So it would have completed eventually, but I think I calculated it would probably take something like 3 years to do the 80,000 by 80,000. Python, if you load 80,000 and a matrix that's 80,000 by 96, and you say core of that data frame, so you compute the correlation matrix, it takes a while. It doesn't like it. And I could not get it to run on my computers. So in this case, I consulted an expert in C++, and he also happens to be my husband. He's sitting right over there. And he made a version of the concordance pair finder that runs in 10 seconds for those 80,000 subject, or 80,000 specimens rather. And essentially the way we did it, it was kind of a joint production. So I put out the genotypes as bit vectors, and he used the SIMD intrinsics in C++ to essentially fit all of the calculations in the L2 cache. So you're looking at sort of 10 or so machine instructions per calculation. So you can really get a lot. Now, I don't have an awful lot of time. I was going to just talk a little bit about that bit representation just because I found it really interesting. I mean, I'm kind of a geek, but and essentially what we did is break each genotype down into 3 bit vectors representing the XX genotype, the XY, and the YY. So each specimen got 3 bit vectors that represented it. And then using this, essentially overlap is an AND of ORs, and support is an OR of ANDs. And so these are very basic relations, and so you can essentially just blast through this and compute them very quickly. So summary, use the right tool for the task. I'm not sure if I've convinced SQL Server is the right tool for the task. Personally, I think it is most of the time. But of course, that's sort of like, to the person with a hammer, everything looks like a nail, right? And where's the machine learning? Okay, I kind of lied in the title, so I apologize for that. But here was my thing. So thank you. Okay, so I see the first one that I see is, do you have to process pandas inside SQL 2017 with Python, or is exporting panda structures to external Python easy? So you can do either. I didn't actually show a demo, but you can run the Python natively in, let me call it up here. This is SQL Server Management Studio, and you can run the Python natively in here on top of the database, treating the tables as data frames. So you can either do that, or you can pull the data frames out of the database and actually compute it, in main memory using Pandas, slice it, dice it, do whatever you want to it. So really, you can do either. Okay, within the wearables research effort, is it possible to identify Parkinson's onset or predict future onset? We certainly hope so. I think we're sort of on the compliance end in that we look at and see whether people are actually wearing their watch. You know, and so it's really kind of, once the data is available to researchers, you know, and it'll be publicly available data pretty much, then they'll have to basically answer that type of question. And so hopefully we can answer that type of question. Is the SNP sampling method unique to your system, or is this a common format across the field of genetic sampling? Well, I'm not really qualified to answer that question, but I think that the fingerprinting is fairly standard. Fluidigming may be proprietary and may be kind of unique in the particular process they use, but I'm not really well enough versed in that. Will any of the wearables measure blood pressure? I'm not sure. Anyway, thank you.